All right. Thermochemistry. This is a two-part unit. This unit, Thermochemistry, is kind of combined with a later unit called Thermodynamics, where we look at all the different thermodynamic units of enthalpy and entropy and Gibbs free energy. This unit, we're specifically looking at heat in terms of energy, Q, heat that's released in reactions through things like coffee cup calorimetry and stuff. We'll do this in physics. Have you done heat in physics yet? You're doing it right now. So there's going to be a lot of overlap here, except they use what, a capital Q for heat, and we use a lowercase q. Certain things are a little bit different. And how we tie that in is the use of delta H, which is enthalpy, which is the heat of a specific reaction. So in physics, you're just solving for Q, how much heat is released when something happens. We're looking how much heat is released or absorbed for a specific mole of a reaction. All right. So to introduce it, we talk a little bit about energy. I'm not going to read all this to you. I think you know most of it. You know what potential and kinetic energy is. What I do want you to know is what this first law of thermodynamics states. And that's law of conservation of energy. Energy can be converted from one form to another, but can neither be created nor destroyed. So we're going to see energy move from reactants to products, back and forth. And in that process, that energy can be used to work. And we'll talk about how chemical systems do work. So we're going to talk about specifically internal energy here in a minute and how to calculate it using heat and work. Down here at the bottom, there's something called a state function. When we hit enthalpy, I will define this more clearly and talk about it, but this is an important property. So for now, just go ahead and circle that, and I'll address that in a couple days. Circle it so when you go study for your test, you'll then know why that's important. Chemical energy. So before we can even start talking about it, you need to be able to define the system and the surroundings. In physics, that's going to vary if they have an engine or if they don't, or they have an adiabatic system or a not, whatever, all that stuff confuses me. I don't know the physics stuff. But in chemistry, the reaction in the beaker, that reaction is always the system. And everything surrounding it is the surroundings. So when heat flows into the system, that is considered to be an endothermic reaction. Heat enters. So the sign on that, does anybody remember? Endothermic? Positive. That's right. In an exothermic reaction, energy is flowing out of the system, and that is a sign of negative. So you did the airbag lab. How did that bag feel when you were running it? It was cold. That's considered an endothermic. Okay, heat was leaving the system, that you could like the surrounding area, to go into the solution to give the molecules energy they needed to do whatever they needed to do. So if something is to the touch cold, now if a reaction's happening, we're going to see some real life examples that are a little strange. But if the reaction is cold to the touch, that's endothermic. If the reaction is hot to the touch, it means heat's being released by the reactants or with the reactants, so that is exothermic. Down here, you have some potential energy diagrams, and you can go ahead and add your little humpy things. You all have seen these before. No matter what level of chemistry you took, you saw these. And these tell us the actual energy of reactants and products. And we can look at the overall energy difference from the products minus the reactants. We always do products minus reactants to get our change in heat, our overall change in the reaction. So in this one, you could do it mathematically. Let's do it with the math first. If I have a low value for product and a high value for reactant, what's the sign going to be? This is going to be negative. Okay? You can also go ahead and just look and ask yourself, I have a really high reactant. Oh, products got really low. Where did the heat go? It left. So heat leaving is exothermic. And the value of our Q is negative. Here, initial final minus initial gives us positive number, so that's endothermic. And just looking at it from reactant to product, little reactant had little energy, all of a sudden reactant had a ton of energy. Where did the energy come from? From the outside in to give those products that energy that is positive endothermic. Okay? So does everyone understand how to find the sign on their cue using potential energy diagrams? This stuff shows up all the time. All right? So your delta H is actually here, the difference right there. Okay? Does anybody remember what the energy from here to here is called? Here to here? Yeah, activation energy. Yep, that's the activation energy, the energy required to get the reaction going. Okay? And we're going to revisit these a little bit at some other point, but most importantly is finding that delta H for this unit. Okay, so what we're going to do is look at these real-life situations, and it shows you here that the system is underlined, okay? So we're going to say if it's endo or exothermic. Your hand, that's the system, gets cold when you touch the ice. Endo or exothermic, from the perspective of the system. Endo. Oh, no, exo. You guys are right, exo. You got to, it's heat. Heat being the thing you're looking at. For your hand to get cold, doesn't heat have to leave? Cold comes in, yes, but we're not measuring cold coming in. We're measuring heat going out. So that is exothermic. So this is what I was saying before, when you touch a reaction and it's hot, it's exo. This is not touching a reaction. We're looking at, because you're in that situation, the system is the beaker. Here, your hand is the system, okay? So when your hand touches the ice, the heat leaves your hand, so it's exothermic. Got it? All right. The ice gets warmer when you touch it, so the ice is the system. The ice is endo, right? It's absorbing the heat from your hand. Water boils in a kettle being heated on a stove. Yep, water is boiling. You're putting heat into the water. So boiling is truly endothermic. Water vapor condenses on a cold pipe. Exo, the gas, for it to get to liquid, has to release heat. Okay, so it is exo. Ice cream. I want ice cream. Ice cream melts. Endo. For the ice cream to melt, it absorbs heat, right? Ice cream will put me in a better mood. I want some Rocky Road or some mint chocolate chip. Yeah. Oh, yeah. That's good stuff. For each of the following, I'm not an emotional eater by any means at all. Yeah, right. For each of the following, define a system and its surroundings and give the direction of energy transfer. We're not going to say exo or endo here. We're just going to say what direction the heat goes and what's the system and what's the surroundings. Methane is burning in a Bunsen burner. So forget that it's in a laboratory. That's not part of it. So what's the system? The methane is the system. The Bunsen burner is the surroundings. Which way is the heat going? Well, I don't want to define it that way because that gets confusing. I just want to know which direction the heat is going, from what to what. From the surroundings to the system, from the burner to the methane. Okay? And here's why. Rui did say it's endo. That's correct. However, when you burn methane, that's an exothermic reaction. So I don't want to go there. Does that make sense? Because we're talking about beginning to end, so yeah, we're just looking at which way the heat is transferred originally. Water drops sitting on your skin after swimming evaporate. This is the system. Water drops, right? And your skin is the surroundings. What happens? Which way does the heat go? Skin to the water, again, from the surroundings to the system. Same exact scenario as the other one. Okay, so as we study in this unit, it is really, really, really crucial that you realize everything we write has got a number and a sign. You look really, really entertained. And I have a feeling it's not chemistry. No, Abby, you got smiles going. Okay. Well, I'm glad it's amusing you that much. The number, to me, yeah, the number is important. Did you solve the problem right? But I don't really, it doesn't mean a lot to me. 576 joules. What does that mean? It's a number, yeah. But what's more important to me is that positive or negative, because that's telling me if heat's absorbed or released. So this sign that indicates direction on any of our thermodynamic terms is just as important. So I want to look at first this internal energy calculation. To find internal energy, I'm trying to pull this down and I can't. We'll just move all of it up. Internal energy's equation is Q plus W. You do need to learn this. It is not on the sheet. Where Q represents heat and W represents work. And we're going to talk about work, reaction and work. We've never done that before, but we're going to talk about it. We know how Q, what Q is, it's heat, and we know the signs associated with that, right? Negative, exothermic, positive, endothermic. So let's talk a little bit more about the work part of this reaction. So here's our Q business. We already know that, right? And then here is our work business. To find internal energy, we need to know how much work the reaction is doing or what's being done on the reaction. So first, let's talk about the sign, and then I'll explain it to you. The system does work on the surroundings. That means the sign on the work is negative. How you can remember that is pretend you're the system. If you are doing work, you don't like that. That's negative, right? Okay, so if the system's doing work, the sign on work is negative. Now, what happens if surroundings do work on the system, like you're getting a makeover or you're getting plastic surgery? That's pretty positive, right? So if work is done on the system, that's going to have a positive sign. So that's how I remember it, because I literally have to think through it that way, because I'm not good at memorizing things. So what does it mean, this work business? There is only one way in the whole wide world that chemical reactions do work. What is the only thing chemical reactions produce that push against the atmosphere? Only state of matter, yeah. Gases, yes. The only way a system can do work in chemistry is literally by producing a gas. So when you were doing the airbag and that bag filled up, it was doing work. That system was doing work because it was inflating the bag against the 1 atm or whatever the pressure was. Okay? So systems do work by producing gas, period, end of story. We don't have motors and all this stuff that they have in physics. We just have these reactions making gases, and if a gas is compressed from the surroundings, then work is being done on the system. Okay? And then we just need to know the signs. Now, how you actually calculate work, that's so you can plug it into the internal energy, is negative P delta V. You're going to need this for physics. You might as well memorize it now. Work is negative P, that's pressure, times delta V, which is change in volume. And it's always final minus initial volume. That delta is always final minus initial. And that's going to make sense. You'll see. We'll talk about it when we get to doing the problems mathematically. We'll end up with the correct sign if we do final minus initial. Now, if you look at the units here, pressure is in atm, right? Volume is in liters, change of volume. So an atmosphere liter, that's not a good energy unit. If we want work, work needs to be in energy. It's joules. So it's a type of energy. So this is a little conversion. Someone asked me if you needed to memorize this. I need to go look at a few years back tests. I don't remember if we had y'all memorize this in the past, and I will find out shortly. But converting these liter atmospheres to joules is using 101.3 joules per liter atmosphere. Okay? So let's go ahead and start doing some problems. All right, which of the following performs more work? What is the formula for work again? Negative P delta V. So a gas expanding against a pressure of 2 atm from 1 to 4. So what's my final volume? 4 minus 1. So that is, we don't really need to convert right now. We can leave it because it's a comparative number. Negative 6 latums, right? Does that look correct? All right, let's look at the next one. A gas expanding against a pressure of 3 atmospheres from 3 to 1, from 1 to 3 actually, so it's final minus initial. What is that? Negative 6 latum. All right, so does it make sense that these things have a negative work? Right, the system is doing work. It's pushing out, and that's a negative thing. So those numbers worked out. And it ends up they have the same work. Okay? All right, now let's play with the internal energy equation to figure out some stuff here. So internal energy, we know, is equal to Q plus W. All right. So we're going to look at an endothermic process. What does that mean? Q is? Positive. That performs work. What is W? Everyone with me? I just plugged in a positive and negative here. Okay? So, what is the sign in our delta E if work is greater than heat? Work is greater than heat. Negative. So, delta E would be negative. So, what does that mean? The internal energy, if work is greater than heat in this scenario, we're not getting enough provided energy from what's given, basically. Internal energy if work is less than heat. Work, so that would mean this heat would be greater than the work. What would it be? Yep, our delta E would be positive. Does that make sense? It's just playing with signs. Okay, let's set up this one. Again, delta E is equal to Q plus W. In this case, work is done. What does that tell us? Work is done on a gas. Sorry, I didn't finish. Work is done on a gas. So work is done on the system. So that's positive. In a process that is exothermic. What is Q? Negative. So in a situation where work is greater than heat, delta E is positive. And in a situation where work is less than heat, or heat is greater than work, negative. So at the end of the day, do I really care if you know exactly how to do internal energy? Yeah, I'm going to ask you some questions on the test on it. But as far as understanding goes, I need you to know what it means to do work for a chemical system and what is happening with our heat and how they're interrelated. And so signage is hugely important. So now let's just go ahead and solve some of these problems. These are super easy now that you know the equations. Calculate the delta E for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. They're not giving you signs in these problems. You have to use the verbiage. So it says an endothermic process. So what is that telling us? Q is positive, so it's 15.6 kilojoules. And where 1.4 kilojoules of work is done on the system. Positive. All right, so all we do is add these up. As far as sig fig goes, how do we round for adding? Lowest decimal. So 17.0 looks like what it is. Mental math. See it? Simple. If you know your signs, you'll be golden. Calculate the work associated with the expansion of gas. So we're looking for the work calculation. What does work equal to? Negative P delta V. Work is equal to negative, they're telling us 15 atmospheres. Delta V, it's final minus initial, so it's 64 minus 46 liters. So in liter atmospheres, what is work equal to 2 sig figs? Negative 270 liter atmospheres. Does our negative make sense? Yes, our gas is expanding against the surrounding, so the system is doing the work. Just to practice, this liter atmosphere is very not acceptable. We want to get it to a more usable unit, which would be joules. So for every 1 latum, we have 101.3 joules. So to 2 sig figs, how many joules is that? 27,000. Negative 27,000 joules of work. Well, let's think about it. Is it? Because kilojoules would be 27 kilojoules, right? Well, let's talk about that, because negative 27,000. Let's do it in something that you guys understand. So this is joules. Does anyone know the conversion between joules and calories? Huh? So it's 4.18 joules per calorie, right? 4.18 joules per calorie. Whoops, per calorie. I think that's it, right? See, I'm going into a world that I don't know a lot about. But a calorie is not a dietary calorie. What's a dietary calorie? When we say I ate 20 calories, what are we really eating? Kilocalories. So for every 1 calorie, well, I should say every 1,000 calories, I have 1 big calorie. That's what we eat. So figure out how many calories that is, translated to something you might understand. Is it a Snickers bar? Let's see. What is it? So the negative tells us, the negative isn't really meaningful when we're doing this. That's just telling us we're using it and not giving it, or whatever. So just 6.5 dietary calories. Is that a lot of energy? No. I pretty much ate it when I ate my cherry tomato. No, it's not that many calories. But yeah, so in answer to your question, no, it's not a lot. Yeah, anyway, I just wanted to make it a little more meaningful of a number. Okay, number 3. That was a total tangent. People at home watching the video are like, why are you doing this, lady? A balloon is being inflated to its full extent by heating the air inside it. In the final stages of this process, the balloon changes from 4 million to 4.5 million liters. That is one hell of a big balloon. By the addition of 1.3 times 10 to the 8 joules of energy. Assuming that the balloon expands against a constant pressure, calculate the delta E. So we know that to get delta E, we need Q and W. Do we have anything right now that will help us solve for delta E? I see something. We're going to need to find something, but I see something right now I can put into this equation. Yeah, the heat, and it says the addition of, so what does that mean? Endothermic, so it's positive. So I can just put that puppy in there, and that's joules. So what I need to do is calculate work, because that's the one thing I don't have. So over here on the side, I'm going to say work is equal to negative P delta V. So work is equal to negative, what's our temperature, our pressure? It's a constant pressure of 1 atm. Change in volume, it's 500,000. So 5 times 10 to the 5th. Is that right? That's 500,000. Because 0.5 times 10 to the 6th, so 5 times 10 to the 5th. And this is liters. All right, so work then would be equal to negative 5 times 10 to the 5th latums. Can I just plug this latum into that equation? What's wrong with it? I've got to be in joules in order to add it. So this is where I need y'all. I can't do this math in my head. So we know that this is going to be negative because the balloon is expanding. 5 times 10 to the 5th. For every 1 latum, I have 101.3 joules. So is it 5 times 10 to the 7th? Negative 5. We're times 10. We're really bastardizing sig figs here, but it's fine. Whatever. As long as y'all get what's going on. Yeah, I just multiplied this by 100 by adding 2 to the exponent. So when we add them up, what is our delta E in joules?
That is 7.9 times 10 to the 7.
Oh, it brought it down, huh? Oh, okay, cool. And the units? Joules. Okay. Questions? All right. Now, I could theoretically stop here, but I want to get a little bit of a jump on this because I'd like to spend more time next time doing calorimetry and delta H. So this unit, this is the big picture. We're going to cover these different ways to find enthalpy. Remember enthalpy? Heat of a reaction is change in delta H. So by the end of the unit, I need you to ask yourself, can I do these? Do I have these down pat? Because you're going to see all of these on the test. So the first one we're going to look at today is stoichiometry. If you see on the board, I'm leaving this up. So today we're just going to look at stoichiometry. This is super simple. You already know how to do this. Consider the combustion of propane. They give you a balanced equation, and here they give you a delta H of negative 2221 kilojoules. I want you to add a per mole here. This is per mole because it's per mole of this whole reaction. For every 1 mole of this reaction, we get negative 2221 kilojoules, meaning that many kilojoules are given off. So there's a stoichiometric relationship. For every 1 mole of these, 5 of these, 3 of these, 4 of these, we give off that much. So you can put this in with stoichiometry just like any other number. So assuming that all the heat comes from the combustion of propane, calculate delta H, in which 5 grams of propane is burned in excess oxygen. Well, that is the equation representing propane being burned. I'm going to start with my 5 grams, and I'm ultimately going to want to mole bridge to that guy. What do I need to be in to mole bridge? Moles, right? So for every 1 mole, well, not because of that yet, 1 mole of propane, how many grams do I have? 42.09 grams. Okay, and now I can mole bridge. For every 1 mole of this, I have that many kilojoules. 1 mole of that on the bottom, I have negative 2221 kilojoules. Now, you don't have to write per mole here because you're saying that. You're saying this many kilojoules per 1 mole of this, or this many kilojoules per 5 moles of that. Whatever number you use, that's already being taken into account right there. This is per mole of the whole reaction. All right, so to 3 sig figs, how many kilojoules do we give off of heat? 3 sig figs. Mm-hmm. 264? Negative 264 kilojoules. Now, I'm not going to write per mole here. Why? Because what? Well, the moles cancel, but I'm talking about theoretically. What is this kilojoules per the 5 grams, right? It's not kilojoules per mole. It's kilojoules per the 5 grams. So that's why we don't include it. Now, the next one, I wish they were all this hard. The enthalpy for the formation of Na2O is shown below. What is the amount of heat released when 1 mole of Na2O is formed? How many did we form here? 2 moles. This is associated with that. When 1 mole is formed, how many do we? Half of it, right? If you struggle with that, you can do stoichiometry. Start with the given in your problem, 1 mole of Na2O. You're in moles. You can mole bridge. For every 2 moles of Na2O, I have negative 828 kilojoules. All right, and so that gives me negative 414 kilojoules. Now this you can write per mole here because that's truly per mole of this guy. All right, I know moles cancel, but that's still how many are given off per mole of the product. So that's okay. Okay, are we good? All right, let's go to the next one. The enthalpy for the decomposition of Fe2O3 is shown above. What is the enthalpy for the following? Oh, this is rough. What are the differences between those two reactions? It's reversed, right? So what do you think? Inverse, we're going to change the sign. We're going to make it negative because what becomes endothermic now is going to be exothermic. And these both should really be per mole of reactions. So. Okay, and this last one, you really don't have enough information to do. You need to be given the heat of combustion of, I looked it up, ethanol, I looked it up last period. The heat of combustion of ethanol is negative 1360 kilojoules per mole. And what that is, negative delta A, it's delta H with the subscript COMB, combustion. Subscript COM. That's the heat of combustion. So the heat of combustion of this guy, determine the amount of heat released when 1 gram of ethanol. Let's go ahead and get a balanced equation. What does it mean to combust ethanol? Add O2, so what are we going to make? CO2 and H2O. All right, so to balance, I need 2 of those, 3 of these. Let's see, 4, 7. Do I need 7 halves, really? Is that right? No, I don't. I forgot about this one. My bad. I need 7 O's. 3 times 2 is 6 plus 1 is 7. Okay, so starting with my 1 gram of ethanol, what do I do next? Convert to moles. For every 1 mole of ethanol, I have 46.08 grams. And then for every 1 mole of ethanol, what do I have? What are we trying to find? Heat released, right? What's my stoichiometric relationship here? Yep, negative 1360 kilojoules. So what's my kilojoules per gram I'm getting here? 3 sig figs will be fine. Negative 29.5 kilojoules. And that's for every 1 gram of methanol combusted. That's even less than the 6 calories we did. No, it's actually more, because that was 27,000, right? Okay, I think that's it. Let me make sure. Yeah, so tomorrow we're going to start on the second bullet point here. Whoa, 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 come back. Calorimetry. So we're done with stoic. You should be stoic masters. Yeah, flippy thing's fun. I can't wait.